This presentation examines Dr. Robert Zubrin's compelling critique of the Drake equation, one of astronomy's most influential frameworks for estimating intelligent civilizations in the cosmos. The Drake equation, developed in 1961, attempts to predict the number of communicative extraterrestrial civilizations in our galaxy by multiplying together factors like star formation rates, planetary habitability, and the lifetime of technological civilizations. However, Zubrin argues the equation overlooks critical dynamics. Civilizations need not arise only once per solar system. They can collapse and re-emerge. Moreover, the equation fails to account for how life and civilization can spread across interstellar space, expanding far beyond their worlds of origin. By challenging these fundamental assumptions, Zubrin reveals why traditional approaches to the Drake equation may drastically underestimate or misframe the question of life in the universe. This presentation explores his key arguments and what they mean for how we think about extraterrestrial intelligence and humanity's future in space. Let's start with a simple premise. Our galaxy contains roughly 400 billion stars. It is about 10 billion years old, and the laws of physics, chemistry, gravity, biology are universal. The same processes that led to life on Earth are not unique to this planet. If the conditions existed here, they exist elsewhere. The real question is no longer whether life is out there, but how much of it there is. For more than half a century, the Drake equation has shaped our thinking about extraterrestrial intelligence. Developed in 1961, it estimates how many technological civilizations exist in our galaxy by multiplying a chain of probabilities, from star formation to planets to life to intelligence to communication. At its core, the Drake equation balances two competing forces: how often civilizations arise, and how quickly they disappear. When we plug in conservative but reasonable numbers, the Drake equation produces a sobering result. Perhaps 400 technological civilizations exist in the entire Milky Way. That sounds impressive, until we realize how vast the galaxy is. Spread across hundreds of billions of stars, the nearest civilization would likely be more than 4,000 light-years away. In practical terms, we are isolated. The galaxy appears quiet, empty, silent. According to Dr. Zubrin, the Drake equation rests on two deeply flawed assumptions. First, it treats life as a one-time accident, something that either happens or doesn't in a given star system. Second, it treats civilizations as static islands, ignoring the possibility that intelligent species might expand beyond their home worlds. Earth itself disproves the first assumption. Life has been wiped out before, dramatically, yet it returned. The dinosaurs vanished, but intelligence eventually re-emerged. Compared to the 10 billion-year lifespan of stars, civilizations are brief. But biospheres are resilient. Given time, intelligence can reappear again and again. Life doesn't roll the dice once, it keeps rolling. Instead of asking how often intelligence appears, this new model asks a different question. How often intelligent life regenerates across existing biospheres? By focusing on mature, life-supporting worlds and the time scale of biological recovery, the equation shifts from probability to persistence. The galaxy is no longer a graveyard of failed experiments. It becomes an engine of continual renewal. When we apply this regenerative model, the numbers explode. Instead of hundreds of civilizations, we arrive at millions. Around 5 million technological civilizations in the Milky Way. That means roughly 1 in every 80,000 stars hosts an advanced civilization. Suddenly, the universe doesn't feel empty at all. But the transformation doesn't stop there. Any civilization that survives long enough will eventually explore and settle nearby star systems. Even at a modest fraction of the speed of light, a civilization's sphere of influence expands like a slow-moving wave. Over tens of thousands of years, this wave reshapes the structure of the galaxy itself. A single civilization doesn't remain a single point. It becomes a cluster. Thousands of stars linked by shared technology and culture. Multiply that by millions of civilizations, and suddenly more than 3% of the entire galaxy lies within someone's sphere of influence. The nearest outpost may be only 100 light-years away. Here we see the contrast clearly. The Drake equation gives us a sparse, lonely galaxy. Vast distances, rare contact, eternal silence. The regenerative model gives us a crowded cosmos, overlapping domains, frequent neighbors, and a galaxy humming with activity. All of this hinges on one uncertain factor: how long civilizations last. Longevity, represented by L, determines whether civilizations remain isolated sparks or grow into enduring galactic presences, and we have very little data to constrain it. If civilizations last only 10,000 years, the galaxy remains mostly empty. At 50,000 years, it becomes crowded. At 200,000 years or more, civilizations overlap entirely. The galaxy becomes fully settled, everywhere touched, everywhere connected. A short-lived civilization leaves the galaxy wild and unexplored. A medium-lived civilization makes contact rare but possible. A long-lived civilization transforms the galaxy into a network, interconnected, communicative, and alive. However you slice the math, one conclusion remains difficult to escape. There's plenty of them out there. Who they are, what they've built, and how long they've been watching, these remain open questions. But the silence may not mean absence. It may simply mean that the universe is far more alive than we ever expected.